just to sort of summarize and move on to the questions, I know people do have more questions. This is some of the achievements we've made in our first year. We took about 11 months to build the machine. We got funded initially in November of '08. So the machine started working in October of '09. And so the first year we were able to demonstrate, confirm what we achieved in an earlier experiment at the beginning of the decade at Texas A&M, which was that we can get these very high temperatures. And we should update this slide because we now have achieved 100 keV, which is the temperature needed to ignite PV11. So we're good in the temperature range. We've greatly increased the efficiency over the last experiment at the beginning of the decade. And we've improved our yield since our first experiments by a factor of something like 10,000. And as I showed you on the graph, we're about 3 to 6 times better than other similar experiments using this device. So this is some pictures. This is a little off-center, but it shows the little plasmoid formed in the center. This is the anode. These are taken by the ICCD camera, which Fred has been in charge of. The ICCD is our single most expensive piece of equipment. It's a $65,000 camera, which takes exposures that are 1/5 of a billionth of a second long. And that's what we need to stop the action that moves pretty quickly. That's sort of a blow up these little plasmoids.
Yeah. So since then we've increased the magnification.
I'm going to sort of skip this one. We can deal with it. Where are we? Basically a little less than halfway there. We've moved up from 25 kilovolts to 35 kilovolts. We have to get to 45. We have to test other electrode lengths, which we think will perform even better. And then we have to install heating so that we can heat the entire device up to approximately the boiling point of water, and so we can go on in the middle of the year to our experiments with PV11. This is just sort of some of the financial indications. We initially raised 1.2 million. We've raised 700,000 of the 900,000 in this offering. And the next phase, we'd need to raise about 20 or 30 million for the engineering phase. So let me end the show at this point, and just, I think it would be good to take questions.
Yeah.
Eric, I was wondering, I was trying to put together your long history here just quickly. So in '01 is when NASA said, gee, we have to get out of this business because we were told, and so,
Right.
And then I heard about Texas A&M, and there was experiments that you've now achieved 15 times better results.
Right, that was when we were still being funded. In other words, this project actually has a very long history. I got interested in the dense plasma focus back in the 1970s when I met Winston Bostic and Vittorio Nardi, who were pioneers of this device working at Stevens Institute here in Hoboken. And, you know, frankly, at that time, I had bought into the propaganda, you know, the tokamak was going to be the thing. It's basically just an engineering, very boring. And they said, well, that's completely wrong. And I had been sort of initially trained in physics at Columbia, particle physics. I got bored with that. But I had not been trained in plasma physics. And they got me very excited about plasma physics and its relation to astrophysics, which was another one of my extremely long-term interests. And I had been interested in the fusion thing even as a child. So it wasn't until basically 1981 that I had enough ideas to start using the plasma focus as a model for the quasar process. Because quasars, by that time, people knew that they had produced these very narrow asymmetric jets. And that sounded like what I had seen from Bostic and Nardi's work. So in that process, which Nardi was kind enough to sort of give me guidance, like basically thesis advisor sort of guidance, I learned a lot of plasma physics, especially from the work of Hannes Alfvén, who's the founder of modern plasma physics. And by the end of the 1980s, I had developed this theory to the point where it looked like it was testable. So in '89, I started looking for funding. And it wasn't until '94 that I actually found that funding and a partner to work with, which was George Miley, who was the chairman of the nuclear engineering department at University of Illinois, Champaign-Urbana. So he was willing to do the experimental work, and JPL, that's Jet Propulsion Lab of NASA, was willing to fund it for space propulsion purposes. So everybody knows tokamak can't fly. It's like flying the Empire State Building. So that was our first experiments in which we did our first successful preliminary tests of these theories in 1994 at University of Illinois. They did not have a big enough machine to test the theory further. And that led to a big problem. NASA was unwilling to fund the construction of the machine. They were only willing to fund our time. So I teamed up with another scientist, Bruce Freeman, and to make a long story short, it took about 7 years to put together the government surplus equipment and an institution, which was Texas A&M, that was willing to pay for putting that equipment together into a plasma focus device. So we used that plasma focus device, still funded by JPL, to do experiments in which we first demonstrated these very high temperatures in 2001. We ran out of money before we could get to PB11. And when we trotted back to NASA with all our exciting results, they told us, that's nice, but we've been zeroed out. And then when we said, well, what about the rest of NASA, we rapidly found out from our colleagues that this was a policy decision. And all of NASA had been ordered to leave the fusion field. DOE was never a possibility because DOE, for reasons that go way back, decided very early on that the tokamak was the thing, and they, in particular, decided not to fund the dense plasma focus. So that left us high and dry, and that's when I started raising money privately. And it took another 7 years, the biblical 7 years, to get that money together by 2008. So this project has really been significantly delayed by funding restrictions. I mean, we came up with some new ideas like this axial field and the quantum magnetic field are ideas from the last 7 years of work. I suspect we probably could have come up with those ideas if we had funding to do this full time earlier. So, you know, we've probably been set back something like a dozen years or more just for shortage of funding.
And that's a really good story. And you mentioned 1994. Wasn't that the same year as the big breakthrough at Tokamak? That they sustained like 1 billion degrees for a second?
That was when TFTR was running. As a matter of fact, well, that was a big story, is that after the 2001 results, we submitted a paper pointing out that in terms of the product of N times tau times T, which is sometimes used as a shorthand measure of how good you are, we had exceeded the results of the tokamak at Princeton. And perhaps unwisely, before that was accepted for publication, I did a press release around it. And that press release got into the hands of a gentleman in Los Alamos. And he was the supervisor of one of the people who worked on the paper with me. And he said, Hank, you have a choice. You can take your name off this paper, or you can find another job. So, oddly enough, Hank decided that he didn't want to be a co-author. And this actually led to a huge blow-up in which my other colleague was also threatened. And basically that paper never did get published because the tokamak people so resented this comparison. To say the least, this was very unscientific behavior, and unfortunately it's not uncommon. People are defending their turf.
Actually, I can speak to that bit. There was one slide I had, which is very good. This is policy to, right now, Ed Sinikowski, he's the Assistant Director of the Office of Fusion Energy Sciences, and his catchphrase is all hands on deck for ITER. So ITER is the big international project that uses the tokamak. But this kind of policy has been going on back in the 70s and 80s. It was, we have to sing in harmony with the tokamak. And here's a quote from Norman Rostocker. You don't get large sums of money without not only making large promises, but also conveying a sense to the whole community that you're on the right track. You can't tell them, I guess it wasn't quite the right track, we should take a different direction. The chances that the money will disappear when it's handled the way it is by Congress are quite good. So changing course is risky. And they're doing the same thing, I mean, because, they're getting closer with their tokamak. But it's very frustrating, so if you want to read more about university programs being shut down, and it's all there.
This is the origin of the problem, is that the fusion program was extremely underfunded prior to the 1970s. It almost didn't exist in the United States. And when the energy crisis came along, some people, and unfortunately I have to say, although it was mainly managers, it was also scientists, made a sort of Faustian bargain. Congress was interested in energy solutions, alternatives to oil, because that was politically popular at that time. But they didn't want something that was basic research. They wanted something that was near term. And the Soviets had just gotten very good results with the tokamak. And basically the scientists and engineers, when they replicated the Soviet work, they decided to go to Congress and say, hey, the science is done, all we have to do is scale this up, it's an engineering project, government knows how to fund engineering projects, that's it. We'll feed into this near-term thing by giving them the tokamak. Now fortunately that was absolutely not true, and people pretty much knew it was not true at the time. The science problems had not been solved. There was no reason scientifically to narrow everything down to a single device. But it got into a vicious circle, because as there were delays, and of course there were delays because the science wasn't understood, this wasn't the best device, they would come back and say, well, problem is we just need more focus on this, So give us more money, and if necessary, you have to cut off all these other people who are working on it. You know, those are dead ends. So over the course, I mean, of a generation, this is 30 years have passed now, more than 30 years. People have dug themselves deeper and deeper into this trench, so that it is now psychologically very difficult. There are honest scientists working in this field who say, look, I'm working on the tokamak, but the field should be more diverse. But they're a small minority. Most people, they feel if they criticize DOE's direction, they're in danger of cutting their own throats and, biting the hand that feeds them. So I think that's how the fusion effort has gotten seriously off track.